It's lesson 20, so we're about halfway there. It is lesson 20 in Math 221 at SUNY Geneseo. This lesson is all about the mean value theorem, which is one of those theorems that's a little bit more important than you think it will be at first glance. So we start with like the junior version of the mean value theorem. The junior version is Rolle's theorem. Rolle's theorem is named, not surprisingly, for Michel Rolle, a French mathematician. Oddly enough, he was a French mathematician who distrusted the calculus as it was being developed. He wasn't quite sure that they had done enough to put it on a firm foundation, wasn't sure if he liked the results. And so, as history would have it, the only main contribution he made mathematically that we still remember is this theorem that's taught in every calculus class ever. Suppose that you have some function, it's continuous and it's differentiable. Continuous on the closed interval, which means it's continuous at the endpoints. Differentiable on the open interval, which means it might be one of these jobbies. It might be one of these jobbies where there's like a vertical tangent at A or B. If there's a vertical tangent, there's no slope. And if there's no slope, then the function is not differentiable at that point. So we're continuous everywhere. We're differentiable everywhere except for maybe the endpoints. If f of a is f of b, then there is at least one number c in the open interval where the derivative is 0. There is at least one number in the open interval at which the derivative is 0. This is actually not terribly difficult to prove, and so we will. If the function is continuous on the closed interval, then f has a max and a min on the closed interval. Then there's two options as to where that max and min occur. If the max and min occur at an interior point, somewhere between A and B, not A, not B, in between A and B, well, then that's great. We know that the derivative has to be 0. Hooray. If it's an endpoint, if the max and the min occur at the endpoints, then the function is a constant. And so its derivative is 0 all the way across. If the max and the min both occur at the endpoints, then the function has to be a constant function. And if that's the case, its derivative is 0 all the way across. So you pick any c and you're fine. What I'd like to do is I'd like to confirm the theorem. Confirm Rolle's theorem for f of x equals x to the fourth minus 2x squared on the interval from -2 to 2. What do we have to do to confirm the theorem? Is the function continuous on the closed interval? Yes, it's a polynomial. Polynomials are continuous. Does the function have a derivative everywhere between -2 and 2? Yes, we can confirm that. Is f of -2 equal to f of 2? Well, yes, we can confirm that. So there has to be some value in between -2 and 2 for which the derivative is 0. So f prime of x is 4x cubed minus 4x. Does that in fact equal 0 at some place between -2 and 2? Yes, it happens at 3 different values between -2 and 2. All of these are between -2 and 2, so we're fine. If I may, assumptions matter. Assumptions matter. If the function is not continuous, then there is not necessarily a place where the derivative is 0. If the function is not differentiable at every point between a and b, then there is not necessarily a place where the derivative is 0. The continuity matters, the differentiability matters. Okay, so time to bring up the big deal. This is the mean value theorem. This is the thing that goes on the index card. This is the thing you want to know. We suppose that f is continuous on a closed interval, differentiable on that open interval. Then there exists some number c in between a and b such that f prime of c is f of b minus f of a over b minus a. And you're asking yourselves, what? What? You have some function. It is continuous and differentiable on some interval ab. Where are these things in the picture? Well, this is the slope of a secant line. It's the slope of this line. Change in y, change in x. It's the slope of a secant line. This is the slope of a tangent line. What the mean value theorem says is that there has to be some place in between a and b where the instantaneous rate of change is the same as the average rate of change. Where the instantaneous rate of change is the same as the average rate of change. Where the tangent line is parallel to the secant line. This is actually not bad to prove. To prove it, we bring in another function. We bring in the function f of x minus f of a minus f of b minus f of a over b minus a times x minus a. That's f of x minus f of a minus this slope times x minus a. And all this is the vertical distance between f and the blue line. That's all it is. This function h is the vertical distance between h and the blue line. That's all it is. Well, h satisfies the conditions of Rolle's theorem. It's continuous because it's a difference of continuous functions. It's differentiable because it's a difference of differentiable functions. And at A, the difference is 0. And at B, the distance is 0. So, for some C in AB, h prime of C is 0. Well, what's h prime of C? We take the derivative, take the derivative, take the derivative. Well, the derivative of that, pretty straightforward. Derivative of that, well, that's 0 because that's a number. And derivative of that is just the slope. So, sorry, that's a C, sorry. There is a place where this thing is 0. And if this thing is 0, then f prime of C has to be f of b minus f of a over b minus a. And we're good. So what does that look like from a mechanical standpoint? Find the C guaranteed by the mean value theorem for g of x equals x squared minus 4x plus 4 on the interval from 0 to 3. Well, it is continuous. It is differentiable on that interval. So there has to be a place where g prime of c is g of 3 minus g of 0 over 3 minus 0. Well, let's consider those separately. What's the derivative of g? The derivative of g is 2x minus 4. we evaluate at C. G of 3 minus G of 0. Well, G of 3, that's 9, minus 12 is negative 3, plus 4, that's 1, minus G of 0. G of 0, that's 0, is 4 over 3 minus 0. So we've got 2C minus 4 is negative 1, and that makes C 3 halves. 3 halves does lie on that interval, and so we know that we're okay. We take the derivative, we set it equal to the slope of the secant line, and we find the value of C that holds. Sometimes we can do it with simple algebra, sometimes we need a calculator to help us out, but in all cases, we set the derivative equal to the slope of the secant line and crank it out. All right. When we get to class, we're going to practice a little bit of these mechanics, and then I have some teaching to do about some real serious consequences of what happens because this thing is true. But that'll happen when we gather in class. All right, see you then.